In this video, we're going to look at the steps that we take to analyze the graph of a rational function. Alright, so let's take a look at one example. So if I define f of x to be 2x squared minus 5x plus 2 all over x squared minus 4, I'm going to first graph that if I want to analyze the graph of this function. And I notice a couple things here. So it seems to be a discontinuous function. And it looks like it's going to have some kind of asymptote. It's still going to have a domain and range. It's going to have looks about one x-intercept and looks to be about one y-intercept. So let's prove that algebraically. The first thing I'm going to do with this function is I'm going to find the domain algebraically. So to remind you, the domain is all real values of x that make the function real as well. So the tricky thing about the domain is really knowing where it's going to be restricted. And for a rational function that has a fraction, especially with an x in the denominator, the rule that I know about fractions is that this denominator cannot be 0. So I'm going to set my denominator not equal to 0, and I'm going to factor. So I get x should not be 2, and x should not be negative 2. So if I'm going to define the domain here, I'm going to use my set builder notation, and I'm going to say x is an element of all real numbers where x is not negative 2 and x is not positive 2. So before I move on and do anything else with this function, I want to express it in lowest terms if possible. That's going to make my life so much easier. So what that means for this function, for this rational function, is I'm going to try to factor both numerator and denominator and see if there's anything that I can cancel. So I'm going to use my factoring method here. I'm going to pull out the things from our last slide. I'm going to see what I end up with. So I have 2x minus 1 and an x minus 2 in the numerator, and I have an x plus 2 and an x minus 2 in the denominator. One of my favorite things to do is to cross-cancel because I have multiplication on both top and bottom. So really, in lowest terms, f of x is 2x minus 1 over x plus 2. So moving forward, I can either use this function or this function to manipulate to find anything that I'm looking for because they're both equivalent to one another, which is a really nice trick. So moving forward, let's actually find the intercepts for f of x. Now keep in mind there are x-intercepts and y-intercepts. So the x-intercepts are when y equals 0, so I'm going to set that equal to 0. I'm going to use the function that I solved for lowest terms on the last slide because that's so much easier to use. And I'm going to solve for where x makes y 0. So when I cross multiply and I do all my fun algebra stuff, I end up with the x-intercept being at x equals 1/2, or you can express it as 1/2 comma 0. So on the flip side of that, I'm going to find my y-intercepts, and I'm going to plug in 0 for x, and I'm going to use the same simplified or lowest terms function that I did for my x-intercepts. I'm going to solve that out. So when I work that out, I get f of 0 to be negative 1/2, or I can express it as an ordered pair as 0 comma negative 1/2, which actually matches the graph that we saw last slide. Alright, so next let's actually try to find the asymptotes for this function using the graph. So it appears that it's going to have a vertical and a horizontal asymptote. We just need to find the values for which that's true. So let's first start with the vertical. So when I look at the graph, I see that this function here is, as it approaches negative infinity on the x-axis, is going to get closer and closer and closer and closer and closer to x equals negative 2. Same thing as the top part of the function approaches positive infinity on the x-axis, it's going to get closer and closer and closer to x equals negative 2. So we can say that the vertical asymptote is at x equals negative 2. So let's check out if there is a horizontal or oblique asymptote. So let's first see if there is an oblique, and I can do that by looking at the degree of the numerator and the denominator. So the degree here is 2 and the degree here is 2. They match, so I know that that can't be oblique, it's going to be horizontal. So let's try to figure out, using the graph, where a horizontal asymptote will lie. So I'm going to use the same process that I used with the vertical when analyzing the graph. So I'm going to look at this this bottom part here, and as it approaches y equals 2, it looks like it's going to run into that horizontal asymptote. Same thing as this top part approaches negative infinity on the x-axis, it looks like it's going to come really close to y equals 2. So I can actually prove that by dividing our numerator by our denominator. And I'm actually going to do that with the lowest terms of my original function, which would be 2x minus 1 divided by x plus 2. So I'm going to divide that out really quickly. So I see that I have a quotient of 2 and a remainder of negative 5. So that remainder doesn't really matter in the context of finding the horizontal asymptote. So that confirms what we already believed, that the horizontal asymptote is at y equals 2, which makes sense for our quotient there. And that's going to do it for this video. Thanks for watching.